Hello everyone. Welcome to the sixth live session of the Semiconductor Devices and Circuits. The course is being taught by Professor Sanjeev Sanjay, and we weekly solve the problems associated with the assignments. So, today we are going to solve the assignment problems related to the metal semiconductor junction. So, since it's already 3:02, let's begin the problem solving session. Let me close the window. Let me turn off the camera first. Okay. So let us start today's session. And actually, I had received one email yesterday to solve one of the problems from the assignment that was posted on the platform, and the deadline is already over. So we will be solving that problem today as well. So I have already told you previously that if you have any query, you can email, and I have been receiving some emails, and I have tried to respond to all the emails, and we have tried to get the solutions or the resolutions for the problems that were posted or that were emailed to me. Although the problems that were associated or related to the present assignments, I couldn't discuss them a priori because of the assignment submission dates. They were not over yet. So after the submission was over, I have already solved some of those problems, and I also tried to provide some insights while whenever someone was feeling uncomfortable in solving any problem. I tried to just give some hints and try to provide some insights into the understanding of the problem. But as already said, I didn't solve the problems a priori because of the assignments being the deadline was not over yet. Okay, the assignment link was still alive. Okay, so let's do the problems on the metal semiconductor contacts. So let's begin with this problem number one, and it says that we have to assume an arbitrary metal, and that arbitrary metal forms a Schottky contact with n-type semiconductor. Okay, so as previously we have already shown you that how when the n-type semiconductor, which has a metal work function much greater than the semiconductor work function. I shouldn't say much, which has greater work function than the metal work function greater than the semiconductor work function. So it looked like this, what we had drawn previously. If this was the metal side, and this was our vacuum level, okay, for example, wait a second, and this was our vacuum level, okay, this is our vacuum level, let us call it vac, okay, and this was the, if for example we consider this to be the separation, that the metal and the semiconductor were separated, if this is the metal side, and the work function of this metal is, let's say, q phi m. I am writing q because we are talking about energies. Okay, so these are the energy band diagrams. Okay, so n type means that they, for the Schottky contact, if we are going to form the n type, if this is the Fermi and this is the valence band, then this will be the separation between the conduction band and the valence band, and let us note it by phi n, and this is the electron affinity. So this was when the semiconductor and the metal were far apart from each other, and then when we brought these two together, we said that the the Fermi level of the system, both the systems are in contact with each other, the system will equilibrate to a particular Fermi level, and the Fermi level in this semiconductor will be lowered, okay, because now there will be electron transfer from the semiconductor side to the metal side, and as a result of this thing there will be the depletion of the electrons, okay, at the interface of the metal semiconductor on the semiconductor side. Be careful about the terminology. Whatever I have said, I have been specific. I have been specific in saying that it will be on the semiconductor side. Okay, we do not, because we do not show the accumulation of electrons on the metal side because it's already having a lot of electrons. Okay, that's why we never drew the energy band diagram with a band bent on the metal side. Okay, so if this was the Fermi, metal Fermi, and what happened now, the Fermi level will be continued for both the systems, the metal and the semiconductor in the equilibrium. And as a result, if this is our interface, okay, so this will be the conduction band, and this whole thing will be the depletion width, xt, okay, depletion width. This is the depletion. Now, this was the barrier, Schottky barrier, because the metal work function was greater than the semiconductor work function, and this was the phi bn, the Schottky barrier, and this phi bn is simply equal to this metal semiconductor junction is simply equal to q phi m. Q phi m is the metal work function minus chi. Okay, so it's simply q times phi m minus chi. So what we can infer from this is, let me use another slide. We can clearly see that this, let me write down for this. This is the Schottky barrier height for metal and n-type semiconductor. Okay, so this is the Schottky barrier height, and you can see from this that neither this metal work function phi m nor chi, which is the electron affinity, okay, chi depend on doping. Okay, so it was said that how does the Schottky barrier height vary if the doping in the semiconductor decreases. So since neither of the two, neither phi m nor chi depend on the doping, so we can clearly see that thus change in doping level in the semiconductor does not have influence on this Schottky barrier height. Okay, I hope it's clear that the doping now, so as a result of this thing, the Schottky barrier height will remain unchanged whenever we change the doping. Okay, so it remains unchanged. Now let's move to another problem. It says that the arbitrary metal has been deposited on a lightly doped n-type semiconductor, and the work function of the metal is much higher than the work function of the semiconductor. So we have been given some options and we have been told to look into the options, and we have been told to find the how we can make this metal semiconductor contact to be ohmic, and we have to assume the contact is ideal. As I previously said in the previous lecture, sorry, I said that if we have these interface states, we can have the Fermi level pinning. The surface states, then this Schottky barrier, it does not follow this Mott barrier rule for the Schottky barrier height. That is, the barrier will not be ideally equal to q times phi m minus chi. It will be pinned to some other value because of these interface traps or interface states that are present in the semiconductor. Okay, so we have been told here to assume that there are no surface states. So this is the assumption that we have to go with the ideal contact. Okay, we have to follow the ideal contact assumption. So when this arbitrary metal is deposited on a lightly doped n-type semiconductor, and the work function of metal is much higher than the work function of the semiconductor. So we have seen previously the metal work function in this case was higher than the semiconductor work function. So how can we enhance this barrier in order to obtain a ohmic contact? So a simple solution for this is, as I have written over here, this ideally a metal semiconductor and type semiconductor junction where this metal work function is higher than the work function of the semiconductor is Schottky in nature. That we have seen in this. Okay, this was Schottky. Okay, this was Schottky in nature. Okay, we have seen this thing. And now in order to make this junction as ohmic, what we have to do, we have to do the doping. Okay, we have to dope the semiconductor heavily, okay, with the same type of impurity. For example, since this is n type, we have to dope it n type heavily. Okay, and as a result of this thing, we will be having what we will be getting. If I draw this again, what we will be getting is, we will be getting this metal. If this is the metal, this is the interface, and this is highly doped, let's say. Okay, if this is highly doped, this is EC, this is EF, this is EV, this is Schottky barrier. Okay, what happens in this case, for heavily doped semiconductor, this will be thin. Okay, this is thin now. Okay, thinner barrier. Since this is thin, the carriers can easily tunnel through, but the condition is that this is thin. It will be thin for heavy dopants. Okay, so this is it. Okay, so what we can say is, we have to dope the semiconductor heavily with n type. Okay, with n type near the contact region. Okay, so the option A is the correct option to go with. Okay, semiconductor has to be doped heavily, degenerately near the contact region, that is the semiconductor interface. Moving to another problem, which says that in a certain Schottky contact we have this negative bias applied. Okay, so the metal is the negative bias is applied on the metal with respect to the n-type semiconductor. Okay, so compared to the equilibrium, what will happen to the depletion region and the peak electric field? So the problem statement is that we have to look into the electric field. Okay, and we have to see what happens to the magnitude of the electric field and the uh, sorry magnitude of the electric field and the depletion rate. So this is a Schottky contact. Again, this is a Schottky contact, and the magnitude or the peak of the electric field is simply given. Since we have done these things in the course itself, they let me write it down simply, as professor has already taught these things in detail. In a Schottky contact, the magnitude of electric field, the magnitude of peak electric field. The magnitude of peak electric field is simply E max. Let me write the magnitude is simply Q times ND. Since this is an N type, that's why we have written ND. Donor impurities. XT is the depletion width times epsilon s, the relative permittivity times the permittivity of the free space will be, this will be simply ES is on the semiconductor side, and the semiconductor material is silicon, so it will be 11.7 times 3.9 times 11.7 times E naught simply. Okay, so this XT, this is the depletion width, and it is given by simply 2 times epsilon s phi bi minus VA. VA is the applied potential by Q times ND. So VA is applied bias. Okay. So for thermal equilibrium, it has been written compared to the equilibrium. Okay. For thermal equilibrium, VA is 0. Okay. So in case of thermal equilibrium, XT at thermal equilibrium, this is not thermionic emission, it is thermal equilibrium what I have written over here. It is, let me write it down, thermal EQ is simply 2 times epsilon s phi bi by Q at D. Okay, this is the depletion width under the condition of thermal equilibrium. Now, sorry, yes, it's correct. Okay, now when negative bias is applied, that is when negative bias is applied, that is VA is negative. So what would happen? So let us write this. VA is some minus times VR, which is the reverse bias voltage. Okay. So what will happen? What will happen to this XT under reverse bias? Under reverse bias is simply 2 times epsilon S pi BI. Minus of minus will be plus times VR divided by Q. So this is the depletion width. Let me write it as equation 2. This is equation 1. And you can clearly see the depletion width xt of RB is greater than xt of thermal equilibrium. Okay, because this there is an extra factor. This is the extra factor plus VR. Okay, this VR is positive, and since we have taken this VA equal to minus VR, and this means that the VR will be positive. So this whole thing is that the depletion width increases as compared to equilibrium case. Since this Emax is proportional to xt, it means that magnitude of maximum electric field for the reverse bias case will be greater than the maximum electric field under the thermal equilibrium. Okay, so it means that xd increases and Emax, magnitude of Emax, also increases for the reverse bias case. So we will select this option, which is option D for this particular problem. Okay, so what we have obtained is that for the negative bias, both the depletion width and the peak electric field which will be at the interface both increase with the increase in the applied bias, because it's simple. The depletion width has increased in order to uh, provide since there will be more uncovering of the charges that will be transferred from the one side to the another side. It is simple that the depletion width has increased, and as a result of this depletion width increment, the peak electric field also increases. Now we have been given some data about a particular metal semiconductor contact type, and we have been told to find the for this chromium metal. As you can clearly see over here, we have been given this chromium metal which is in contact with the n-type silicon. Okay, this chromium metal is in contact with the n-type silicon, and the semiconductor is doped with the concentration of 10 to the power of 17. Okay, sorry. And we have to calculate the Schottky barrier height and the built-in potential. Okay, and we have to use the following parameters. First of all, the work function of the metal is given, the electron affinity of the silicon is given, the band gap of silicon is given, the effective density of states at the conduction band edge and the effective density of states at the valence band edge are given, and the dielectric constant, relative dielectric constant of silicon, although it's 11.7, but in this problem we have been told to take it to be equal to 11.9. So let's try to evaluate let us first draw the this energy band diagram, which will start with the Fermi level on the metal side. Let me draw this interface. This will be semiconductor side, and since this is n type, this will be my conduction band, this will be my Fermi. Okay, and similarly this will be my valence band. Okay, since the metal work function is greater than electron affinity, and we can clearly see it will be greater than the semiconductor work function, because the material is doped or to the concentration up to the concentration of 10 to the power of 17. Okay, so it will be much higher than the middle of the band gap. Had it been in the middle of the band gap, what we could have said is we could have easily said, let me say that if 1.12 is the band gap, it will be divided by 2, it will be simply 0.56. Okay, if it's 0.56, then if I add it to the electron affinity, which is 4.05, it will be 4.61. So still, even if the material was intrinsic, only then we could have the ohmic contact. Okay, let me write it here, that this Eg by 2 is simply 0.56. So chi plus Eg by 2 is simply 4.61 electron volts. So for approximately intrinsic material, intrinsic silicon, we may had we may have we may had sorry we may have been able to get ohmic nature. Okay, ohmic nature. But the thing is, since this is the you can say this is doped n type, and as a result of this thing, we will not be having the ohmic contact. We will be simply having the Schottky contact. So there will be net transfer of electrons from the semiconductor side to the metal side, and as a result of this thing, we will be having the band bending. So this similar thing will happen to the vacuum level as well. Okay, this is the vacuum level. This will be the semiconductor electron affinity. Okay, let me write it as chi, and this will be the metal work function Q phi m. This will be the Schottky barrier. Okay, Q phi Bn. This will be the difference between the Fermi and the conduction band H, and this will be my Q phi Bi, which is the built-in potential. Okay, so this is our metal side, this is our n-type semiconductor. Okay, so it means now the Schottky barrier height is simply Q phi Bn is simply Q times phi m minus chi. So It is simply Q times phi m. Q times phi m is 4.5 and electron affinity is 4.05. So as a result of this thing, we will get it to be equal to 0.45. Okay. Yes, it is 0.45. 0.45 electron volts. So we have got this to be equal to the Schottky barrier to be equal to 0.45 electron volts. Okay. And so now from the energy band diagram, we can clearly say this Q phi Bn is sum of two things, which is the built-in potential and the difference between the conduction band edge and the Fermi level. Okay, so we can easily say that from energy band from this energy balance using potential or energy balance using energy balance, this Q phi f plus times this Q built-in voltage, built-in potential is simply equal to Q phi Bn. Q phi Bn we found out previously. Now this can give us the value of Q phi Bi to be equal to simply phi Bn minus phi f. So phi f is simply kT, which is at now it is at 300 Kelvin, so it will be 26 milli electron volts times ln of Nc is the effective density of states in the conduction band edge divided by Nd. So it will be simply 0.026 ln of Nc. Nc is having the value of 2.82 into 10 to the power 19. 2.82 into 10 to the power of 19 divided by doping is of the order of 10 to the power of 17. So let me calculate this value. So let me calculate this value. It will be 2.82 into 10 into 100. So it's ln of 282. It is simply ln of 282 times 0.026. So it's 0.15. Phi f is 0.15 volts. Okay. So we have found out this value of phi f, and now from this phi f we can, let me use another pen, so it will be phi bi now simply equal to 0.45. So electron volt and electron volt we have cancelled out, so we have simply set it to be equal to 0.45. It should be volts. Okay, we have cancelled out this thing, so it will be 0.45 minus 0.15 and it is 0.3. So built-in potential is simply 0.3 and the Schottky barrier is 0.45. So 0.45 and 0.3 is the required answer. Okay. So now let's move to another problem, which says that uh, we have to now consider the metal semiconductor junction in the previous question, and instead of n-type doping we are now having the p-type doping, that is acceptor. Now we are having acceptor concentration of the order of 10 to the power of 17. So now what I had previously said, that for the metal semiconductor contact in N type, when phi m is greater than phi s or even chi s, we had Schottky contact. For now, reverse is the case over here, because now we have this metal Fermi, which will be for this p type. It will be above than the Fermi level of the p type semiconductor. So as a result of this thing, we will be getting the Schottky contact for the p type. Now the case is for the p type. So if I let me draw the energy band diagram itself, so that it will be clear to you. So if this is the interface, okay, if this is the interface, this will be the Fermi level on the p side, and it will be closer to the valence band as compared to the conduction band, since it is p type. Okay, p, okay, this total is the Eg, and this is the Q phi f. Actually, I could have written Q phi f n in the previous case and Q phi f p in this case, but it's okay to go with. Okay, so the metal work function has to be with respect to the vacuum level. Okay, if this is our vacuum level, so if this is our vacuum level, this will be Q chi, and this will be our metal work function Q for m. And as a result of this, because there will be now the depletion of the holes at the interface, because now the holes will have moved from the p type and it would have gone into the metal side. So as a result of this thing, we will be having this band bending, and in total we will be having the built-in potential due to this equilibration, and we will be having the Schottky barrier Q phi Bp. Now on the semiconductor metal metal semiconductor, now semiconductors p type metal semiconductor interface. Okay, so actually I should have drawn it like this. For your reference, let me draw it in the red color. So if this is your vacuum level, this was our vacuum level, and the metal work function in the previous case, as it was drawn in the previously, it was 4.5. okay, it is 4.5 electron volts, and what we had seen, that the electron affinity was 4.05, and the middle, if I draw the EI is the middle of the band gap. Sorry, if EI is the middle of the band gap, oh sorry, what is that? I'm really sorry for this. So if EI was the middle of the band gap, it would have been present over here, and this was 4.05, and as I had written it previously, this would have been 0.56 electron volt, simply Eg by 2. Okay, and EV would be somewhere here, and the Fermi will be somewhere here. Okay, what would happen in this case is that there will be the movement of electrons from the metal to the semiconductor. So as a result, if this is the metal side, this is the metal side, this is the semiconductor side. So as a result of this thing, what we have been able to infer is that this means that there will be the transfer of the carriers of the electrons from the metal side to the semiconductor side, and as a result of this thing we will be having the accumulation of electrons on the metal semiconductor interface. So that's what I have drawn over here. This is my metal side, this is my semiconductor side. Okay, so now from this energy band diagram we can clearly infer that this q phi b plus this q phi m is simply q chi s plus eg. Okay, we can clearly say that this q phi b on p side plus q phi m, sorry, or not on p side, on metal side, is simply equal to q chi plus eg. Okay, using potential balance or energy balance. Okay, so from this phi bp is simply now chi q chi plus g minus q phi, and it is simply chi was 4.05 electron volts, eg is 1.12, and q phi m is 4.5. So it is 4.05 plus 1.12 minus 4.5, it's 0.67. So it's 0.67 electron volts for the Schottky barrier. Okay, sorry, now so we have got the Schottky barrier. From this now we have to find the built-in potential in this problem. Okay, so the built-in potential as previously solved will simply be, for this now on this p-type contact, it is simply this q phi bp plus equal to q phi f plus q phi bi. Okay, so it is simply, for this built-in potential, we can say that q phi bi plus q phi f is simply equal to q phi bp. Okay, so phi f is kt q ln of nv by na, simply 0.026 ln of nv. Nv is 1.83 into 10 to the power of 90. It is 1.83 into 10 to the power of 19 divided by Na is 10 to the power of, 10 to the power of 17 per centimeter cube. So it is simply ln of 183. So ln of 183 is simply 5.20 into 0.026. It is 0.14. Okay. Okay, it is 0.14. So phi bi is simply phi bp minus phi f. It is 0.67 minus 0.14 is simply equal to 0.53. Okay, so it is simply equal to 0.53 volts. Okay, it is simply equal to 0.53 and 0.67. So option C, 0.67 and 0.53 volts. Okay, now moving to another problem which says that we have to consider the, wait a second, we have some water. Says that we have to consider this chromium metal semiconductor contact with n-type, and same as in question 4, and we have to calculate when the junction is reverse bias. Okay, when the junction is reverse bias with 5 volts, what is the depletion layer width and what is the electric field at the interface. So it will be the maximum or the peak electric field that we have to find out. So what do we need for this, sorry, for this depletion width? The depletion width is simply 2 times epsilon s phi bi minus VA is the applied bias, by Q times ND. Okay, let us look let's go to the question 4 and see what values we need for this problem. This phi bi ND is 10 to the power of 17 per centimeter cube. So ND is 10 to the power of 17 per centimeter cube. We need this phi bi. I guess we found out in the previous problem, and it was zero point 0.3 volts. Okay, and it is 0.3 volts phi bi, and now we have been given VA is minus 5 volts because reverse bias. Reverse bias. So it means that in general xt is 2 times epsilon s is, it was given, epsilon s was given in the previous problem. It was, we had to take this to be equal to 11.9. 11.9 times the 8.85 into 10 to the power of minus 14. So what I was saying previously was that this epsilon s is 11.7 times the epsilon naught, and for silicon dioxide it is 3.9 times the epsilon naught. Okay, so it is uh, now epsilon naught is having the value of 8.85 into 10 to the power of minus 14. So this VBI or phi BI built-in potential is 0.3, and the reverse bias is minus 5. So minus and minus will be plus, it will be plus 5 divided by Q and D. Q is 1.6 into 10 to the power of minus 19, and ND is 10 to the power of 17. So let's solve for this. It is simply 2 times 11.9 times 8.85 into 5.3 divided by 1.6 into 10 to the power of minus 14, and 2 will go above. It will be 10 to the power of minus 12, 697, 697.7. So under root of 697.7. So it is 0.26 micrometers. the depletion width. Okay. Now the electric field, for the electric field at interface is simply at x equal to 0 is q times nd xd by epsilon s. So it is simply 1.6 into 10 to the power of minus 19 times nd was 10 to the power of 17 per centimeter cube. Xd is 0.026 into 10 to the power of minus 4 meter. Okay, sorry, centimeter, divided by 11.9 into 8.85 into 10 to the power of minus 14. So this is in volt per centimeter. Okay, this will be in volt per centimeter. So let's solve for this. 1.6 into 0.26, 11.9, 0.85, it is 39 or 3.95 into 10 to the power of 5 volt per centimeter. So this is the E value of the electric field. So 3.95 into 10 to the power of 5 and 0.26 micrometer. So the option A is the correct option to go with. Okay, so we will be selecting option A for this. Now moving to another problem, which says that we have to consider this metal, which is this chromium. This chromium is coming again and again, so we have to be careful now that we have to use the metal work function same as the previous case, okay, which was 4.5 electron volts. So it is simply this metal semiconductor contact, same as in question number 4, and this is again subjected to the reverse bias, and we have to calculate the potential drop across this semiconductor, and we have to also calculate the junction capacitance per unit area in the units of nanofarad per centimeter square. It is nanofarad. Okay, so let us say that what is the built-in potential or the potential drop across the semiconductor at thermal equilibrium. So at thermal equilibrium, the potential drop across the semiconductor is simply equal to the built-in potential. Okay, and built-in potential is simply phi bi, and it is equal to 0.3 volts, and it is for the thermal equilibrium case. Okay, now we apply a reverse bias of minus 5 volts. So this potential drop. So this potential drop will appear across the semiconductor, because they drop in metal side. Metal will be negligible. Negligible. Okay. So the drop in semiconductor is simply phi Bi minus Va, and it is simply zero point 0.3. Minus of minus will be plus 5. It is 5.3 volts. Okay. Now the capacitance, we need to find this junction capacitance per unit area. Okay, which is the depletion capacitance per unit area in the reverse bias. So the junction capacitance, junction capacitance wait a second, I need to check this video first. So the junction capacitance per unit area, okay, this junction capacitance per unit area is simply now Cj equal to epsilon s by xt. It is simply 11.9 into 8.85 into 10 to the power of minus 14. Xt is, it came out to be equal to 26 micrometers. Okay, so it is 0.26 into 10 to the power of minus 4 centimeter. Or simply, let's solve for this. It is simply 11.9 into 8.85 6. It is 40.5 nanofarad per centimeter square. So the option C is the correct option to go with. Okay, so option C is the correct option to go with. Now moving to another problem, which is actually this was the problem which was posted, or which someone had emailed to me, and uh, they had told to solve for this problem in the live session. Okay, so let's see how we will solve this problem, which says that we have a capacitance of a Schottky diode. Okay, the Schottky diode capacitance is given by the relation 1 by C square is A minus B times V, where this V is applied voltage and A and B are constants. Okay, so we have to calculate the built-in potential, and we have to calculate the donor concentration. Okay, so let us first see how we solve for the capacitance. Okay, The junction capacitance is given by simply C equal to epsilon s A by xt. Okay, but we know xt is the depletion width and it is equal to 2 times epsilon s phi bi v by q and d. So the C is simply epsilon s A by 2 times epsilon s phi bi v. This is under the square root times d, or simply it is 1 by C is simply 2 times epsilon s phi I minus v by epsilon s times A. This is under square root and this q and d is also under square root. Now squaring both sides, what we get is we get 1 by c square is simply equal to 2 times epsilon s phi bi minus v. 2 times epsilon s phi bi minus v by epsilon s square a square times q and d. So this epsilon s will go with this thing and we will be left with 1 by c square 2 times phi bi by epsilon s a square q and d. And if we try to compare it with equation 1, we can separate the two parts to be equal to 2 times phi bi by epsilon s a square q and d minus 2 times v by epsilon s a square q and d. So comparing equation 2 with equation 1. So let me call this equation 2. Okay, so if this is our equation 2, so it would simply see we will simply see that a is equal to a is equal to 2 times phi bi by epsilon s a square q and d, and b is simply equal to 2 by epsilon s a square q and d. Okay, so what we were required to find, this phi bi and nd in terms of a and b, or in terms of the coefficients that were given to us. So phi bi is simply epsilon s a square q and d by qa. So phi bi is epsilon s times a square q and d. A by 2 is phi b. Okay, and and nd is simply 2 by epsilon s a square qb. Nd is simply 2 by epsilon s a square. So let's check the options. 2 by epsilon s q times a square. This option seems to be matching, and the other is epsilon s a square q and dA. Epsilon s a square q and dA. And this option is also matching. So we will go with the option B. Okay. So overall, we have been able to solve this. So whosoever had asked to solve this problem, they can go through this video lecture, and they will find the solution for this problem, since the assignment deadline is already over. Now moving to the next problem of this today's session. It says that we have a metal semiconductor contact. Again, it is metal semiconductor contact, and this metal semiconductor contact is made with, this time we do not have chromium, but we have gold. Okay, it's gold this time. So this gold is having the metal work function to be equal to 5.1. Okay, it is having the work function to be equal to 5.1, and the doping concentration is 10 to the power 15 per centimeter cube, and the metal is kept at 5-fold. Okay, and the metal is kept at 5 volts below the semiconductor, and we have been told to look into the electric field in the semiconductor, which is at a distance of 1 micrometer from the junction, and all these things are happening at 300 Kelvin. The effective density of states at the conduction band edge are 2.82 into 10 to the power of 19, and the electron affinity is 4.05 for the silicon, 4.05 electron volts, and the relative permittivity of the silicon is 11.8. So, as already done in the lecture notes, as professor has already taught us, the electric field inside the semiconductor for the metal semiconductor Schottky contact is simply, as a function of x, the position is simply q times nd by epsilon s x minus xt. Xt is the depletion width, which we will achieve because of this reverse bias, and x is the position in the, you can say, in the semiconductor from the interface. Okay, if this x is 0, it would mean that we are looking into the electric field at the interface, that is metal semiconductor interface, and it will be maximum at there. So now this problem states that we have to find out the built-in potential for this junction, and we have been doing this quite long now. That this simply from the energy band diagram, if I have this in this Schottky contact, it would simply be phi bn minus times the phi f, and phi f is simply kT by q. Ln of Nc is the effective density of states at the conduction band edge by Nd. Nd is the which the concentration of the dopant atoms, okay, per centimeter cube. So this phi bn is simply uh, equal to the q phi m minus chi, which is simply, let me write down this to be equal to phi m minus chi, and since we are at room temperature, kT by q is simply 26 milli electron volts. Ln of Nc, Nc is given to be equal to 2.82, into 10 to the power of 19, and Nd is 10 to the power of 15. Phi m is 5.1, okay, and chi is 4.05. Okay, so let's solve for this expression which is in ln. It will be simply 2.82 into 10 to the power of 4. It is ln of 2.82 into 10 to the power of 4 times 0.026, which is simply coming out to be equal to 0.266, and 0.266, 5.1 minus 4.05 minus 0.266 is 0.78. So the built-in potential is 0.78 simply. Okay. Okay. So this is the built-in potential what we have got from this expression. And now let us put the, let's use this phi bi value for the xt expression. So if we use this for this expression, it would simply mean we have to use electric field at 1 micrometer is simply equal to Q times Nd, which is 1.6 into 10 to the power of minus 19 times the doping concentration of the order of 10 to the power of 15 by epsilon s is 11.8 into 8.85 into 10 to the power of minus 14 into, this is 1 micrometer, which is 10 to the power of minus 4 centimeter, minus xt. Xt is simply 2 times epsilon s, which is 2 into 11.8 into 8.85 into 10 to the power of minus 14 times phi bi minus Va. Va is minus 5 volts. Okay, it's written over here. It's written over here. Okay, sorry, it's not encircling this thing. So it was written over here. The metal is 5 volt below the semiconductor. Okay, so it means that, sorry, wait a second. Now I guess it should work. I don't know what has happened to this thing. We restart this. Okay. Okay. Let us write down again this thing. So Va is minus 5 volts. So it is simply phi Bi plus 5.78 plus 5 divided by Q times the Nd, which is 1.6 into 10 to the power of minus 19 into 10 to the power of. So I guess this is a lengthy calculation, and you will be able to do it. And I have followed the methodology which I should have followed, and you will be getting one of the correct options from this after solving for this expression. You have to just plug in the values. So in today's lecture, let me recap everything what we have done in today's lecture. We started with this metal semiconductor junction, and we said that whenever we make the contact, considering the ideal contact, okay, I'm not talking about the interface states. If there are interface states, then there will be the Fermi level pinning. So neglect all the interface states that are present on the semiconductor side. Okay, so ideally we will follow the Mott barrier. Okay, so the Mott barrier was given by simply when we solved for this energy band diagram, we said initially the metal and semiconductor were far away, but when we brought them closer, we will ideally be getting the Schottky barrier to be equal to Q phi m minus Q chi. That is the difference between the metal work function and the electron affinity, provided we are able to maintain a zero gap between the metal and the semiconductor. Okay, in realistic scenarios there will be some gap between the metal and the semiconductor, and that gap will also result in the fluctuation of this metal semiconductor Schottky barrier height. Okay, so neglect that as well. Okay, we neglected two main things, that is the delta, which is occurring or which will be present in the real life scenarios when metal and semiconductor will make contact, and also we neglected the interface states, and as a result of this thing we got the metal work function and the electron affinity dependence of the Schottky barrier. So the Schottky barrier depended on only on these two things, and both of these things they do not change with the doping. Metal work function is the material property and it won't change with the doping. Okay, and also the electron affinity, it is the material property and it won't change with doping. So we said that it will remain unchanged, and then we moved to the another problem, and what we said that we wanted to make the Schottky contact as ohmic contact, and for that what we said is we will dope the semiconductor side at the interface very heavily, and as a result of heavy doping what we will get is we will get a thin Schottky barrier, and the carriers can tunnel through from the metal to the semiconductor side. Okay, then now what we did is we solved for the Schottky barrier, metal Schottky contact under the reverse bias case, and we found out that the electric field and the depletion width both increase when the negative bias or the reverse bias is applied to the Schottky contact, metal Schottky contact, and as compared to the thermal equilibrium, both were greater than the thermal equilibrium case. Okay, similarly then we looked into the contact problems which were we solved for the Schottky barrier heights for the n-type semiconductor, and then for the p-type semiconductor we followed the same. Okay, and then afterwards what we did was we found out the electric field at the interface. Okay, uh, for this metal semiconductor contact, and then we did the same to follow the junction capacitance, and on that junction capacitance we built another problem where we solved the junction capacitance for a Schottky diode in terms of the constant coefficients which were provided to us. We found out the built-in potential and the doping concentration in terms of those coefficients that were given to us. Okay, and then we found out the electric field expression at any position along the metal semiconductor junction from the interface, and at 1 micrometer from the junction we found out that the electric field will have some value, and that value we found out using the same expression. Okay, so I guess that's it from my side for the today's lecture, and I guess we are having no questions as well because the audience is there is no audience, so we can end today's session, and I have let me be clear that the problem which I was asked to solve in the yesterday, I guess in yesterday's email, I have solved that problem, and they can look into the today's video lecture, and they will find the solution for that problem in the today's lecture itself. Okay, so I guess that's it from my side. Thank you.